Hey math fans, welcome to the last lecture of chapter 3, where we're going to talk about and prove the second of the Borel-Cantelli lemmas. Okay, so we have A1, A2, an infinite sequence of independent events, and if you'll remember what that means, I defined it in the last video, basically where the partial sequences all have n independent events for any size n. And let's go ahead and define P sub k to be the probability of event A sub k. And finally, suppose that the sum of all of those probabilities from k equals 1 to infinity diverges. So it's equal to infinity. Okay, then we have that the probability that infinitely many events occur, namely A1, A2, etc., occur is 1. That is certain to happen. And it kind of makes sense, right? I mean, if this sum diverges, then clearly, the probabilities are going to be non-zero for some k onward to infinity. Okay, so I guess this doesn't have to be a 1, but from some finite point onward, then it does have to occur. Okay, let's go ahead and prove this. We're going to use a lot of machinery in here, but hopefully we have some useful things that we're going to use. Okay, so proof. Kind of like before in the first Borel-Cantelli lemma, we're going to go ahead and let B be the event that we want. So B is going to be that infinitely many events. Okay, so A1, A2, etc. occur. Okay, we're also going to go ahead and define B sub n as the union for k bigger than or equal to n of A sub k. Okay, so this, you can think of this kind of as like the union of all the a's from some point k onward. Okay. And the reason that we define that is now we can indeed express B in a little bit more mathematical way as the intersection over all such n's. You can think of n as like a threshold, but over all such n's of the B sub n's. Okay, or you could think of this as a limit soup if you're familiar with that from analysis, but if you're not, that's okay. It's going to be the intersection over all of these unions where k is bigger than or equal to n of A sub k. And I kind of defined it in the same way in the first Borel-Cantelli lemma, so if this notation kind of confuses you, you might go back and watch that video for a refresher. Okay, so to show that the probability of B is equal to 1, remember we're trying to show that infinitely many events occur with likelihood 1, we're actually going to show the opposite. We're actually going to show that the probability of the complement of B is 1 minus 1, which is just 0. Okay, so again, keep that in the back of our mind. So that's what we're trying to show. Okay, so to show that, we're going to go ahead and first consider what the complement of B even looks like. So what would B complement look like? Well, if B is the intersection of all of these, then B complement would look like this, which is going to equal the union of all n of the complements of Bn, where this is, of course, by De Morgan's laws. Okay. And we know that the probability of a union is less than or equal to the sum of the individual probabilities. Okay. So we have that the probability of something that can be written as a union, right, since this is technically a union of events, that has to be less than or equal to the sum over all n of the individual probabilities b sub n. The reason for that is the union is naturally going to have some overlap. So taking the probability of that union is always going to be less than or equal to adding up all of the different parts and possibly adding those overlaps 2, 3, infinitely many times, whatever have you. Okay, so, all right. So that's what we have. And again, we're trying to show that the probability of this complement, B complement, is equal to 0. So how are we going to do that? Well, we're essentially going to use the squeeze theorem, and we're going to show that this has to be 0, and this has to be 0. So it's squeezed in between 0 and 0, which means that the probability of B complement has to be 0. So how are we going to do that? Well, remember, B was expressed in terms of the Bn's, so let's talk about the Bn's. So note that Bn complement, which is the same as, k bigger than or equal to n of, now we're getting into the a sub k's complement. Again, by De Morgan's laws, that's just going to be the intersection, where k is bigger than or equal to n of the a sub k's. Okay, and again, that is by De Morgan's. All right, and now that we have that relationship, we're almost good to go. We know that for k bigger than or equal to n, we're intersecting over those. Well, clearly that's actually going to be a subset of, if I just restrict this, instead of looking at, k bigger than or equal to n, let's just go from k equals n to some finite value, maybe n plus m, where m is arbitrary. Okay, so, and this applies for all m. Right, so, for instance, let's say that n is equal to, say, 4, for instance. Well, then this would be the intersection of, a4 complement, a4 complement intersect with a5 complement, intersect all the way to infinity. Well, that's going to be a subset of just starting from 4 and intersecting that with some sort of threshold. Okay, so instead of going off to infinity, maybe we're only going to intersect up to some, a100, for instance. Doesn't really matter what that is. But clearly this is going to be a smaller set than this, because here we're at least stopping the intersections. Okay, so that's why we have that subset. And now that's going to be pretty useful for us, because now if we look at the probability of Bn complement, that is going to be now a probability of, well, it's going to be a probability of this intersection of a sub k's. But since this set is a subset of this set, the probability of this is less than or equal to the probability of that. So we have that this is less than or equal to, or it's bounded above, by the probability of, from k equals n to k equals n plus m of the a sub k complements. All right, now, this is where we're going to kind of use a result that you're going to kind of prove to some extent. Now, the a sub k's are independent, right? So if I have the intersection from, say, k equals n to n plus m of just a sub k's, well, there's no doubt that that's just going to be probability of, sorry, should I have been putting n? I think I should have been putting n, actually. No? No, I'm okay. Never mind. Okay, but this is going to equal, of course, an plus 1, and then finally probability of n plus m, right? It's just the product of all the probabilities, if all the a sub k's are independent, which they are. But we didn't really talk about the complements. Well, it turns out that if all a events, or all the a sub k's are independent, so are the complements. Okay, so similarly, this is actually going to go ahead and imply that this will be equal to, okay, this right here, it will be equal to probability of an complement times the probability of an plus 1 complement times the probability of a n plus m complement. Okay. And that is because independence of events implies that the complements are also independent. Okay, so that's going to be an exercise for you. And I'm only going to have you do it for 2 events. And that will actually be in the exercise set. So basically, if A and B are independent, that implies that A complement and B complement are independent. And then the result for any arbitrary number will follow from induction. Okay, now comes the fun part. This is the probability of a complement, which is 1 minus the probability of an event. So we have that times 1 minus the probability of an plus 1 times times 1 minus the probability of a sub n plus m. Why is that fun? Well, remember the last video, I asked you to prove a lemma. I asked you to prove that 1 minus a number x that's positive, and probability is a positive number, or at least it's non-negative, that is less than or equal to e to the minus x. Let's use that. Because remember, we're trying to bound a sum above. Okay, so that's going to be less than or equal to, well, e to the minus, well, let me write it like this, actually, because this notation is going to become kind of cumbersome. So this is, remember, lowercase p sub n, 1 minus lowercase p sub n plus 1, times 1 minus lowercase p sub n plus m. That's just the notation that we used. Now that's going to be bounded above by e to the minus pn times e to the minus pn plus 1 times e to the minus p sub n plus m. Okay, and this is by the fact that, 1 minus x is bounded above by e to the minus x. Now we're almost done. So this is a bunch of exponentials being multiplied together. So remember, properties of exponents, so that we can add those together. And in fact, when we add those together, we're going to get a sum starting from k equals n to n plus m of p sub k's. Okay, so let's just summarize what we've done. So summary of what we've done so far. We've shown that the probability of Bn complement, we've shown that probability of Bn complement is less than or equal to e to the minus and then the sum from k equals n to n plus m of the p sub k's. Okay? I'll do this last part in a different color. All right, so note that, first of all, we have that the sum from k equals n to n plus m of all these p sub k's. Well, remember, m is arbitrary, and m could be anything, and this still needs to hold. Well, as m approaches infinity, then we're going to have the sum from k equals n to infinity of all the p sub k's. And by hypothesis, that is going to approach infinity. Right? That was the first thing that we said right here, that the sum of all of them is infinity. And if we subtract finitely many, that doesn't matter. We're still going to get infinity. Okay? So, and this is, of course, as m goes to infinity. Okay, so that occurs by hypothesis. Okay, well, clearly if a sum is going to infinity, well then e raised to that sum is also going to go to infinity. Okay, now if you have a sum that's going to infinity, 1 divided by that is going to go to 0. That's kind of a standard result in analysis, right? So, you know, if limit as n approaches infinity of a sub n is infinity, if that diverges, then you can show that limit as n approaches infinity of 1 over a n is equal to 0. That's a standard exercise. Okay, I'm just going to leave that there. But that means that if I take 1 over e to the sum k equals n to n plus m of the p sub k's, that's going to go to 0. And oh, by the way, 1 over e to some power is the same as e to the minus sum k equals n plus m of the p sub k's. Well, where have we seen that before? Well, we've seen that right here. Same exact thing. So, what we have is by letting m go to infinity, we have that the probability of the b sub n complement, that's less than or equal to e to the minus sum from k equals n to n plus m of the p sub k's. And as m goes to infinity, I'd like to remind you that this is tending to 0. And by definition, probability is non-negative. So this has to be greater than or equal to 0. So by the squeeze theorem, again, a lot of analysis results, so I apologize, but hopefully intuitively it makes sense that if this side is going to 0 and this side is going to 0, this has to go to 0. There's just no other way. So by the squeeze theorem, the probability of b sub n complement is equal to 0 for any n that you choose, for every n. Okay, so that means that the probability of b complement, which I'll remind you was less than or equal to the sum from over all n of the probability of the b sub n's complement. Again, probability is non-negative, so we have that we're summing up a bunch of zeros. Okay, so that's going to go to 0. And applying the squeeze theorem once more, we get exactly what we wanted. So thus, the probability of b complement is equal to 0. So that implies that the probability that infinitely many events occur is equal to 1. Okay. So a lot of machinery in this proof, a lot of good things, I think, especially this exercise. And again, I am going to include that in the exercise set for 2 events. But that is the second Borel-Cantelli lemma. Go back to the first Borel-Cantelli lemma video for some good examples. But yeah, so if you have an infinite sequence of independent events, and you know that the sum of all those probabilities is infinite, then you absolutely know that infinitely many events will occur. All right? Thank you so much. I'll see you in the next video.